Okay, so today I'll be talking about my class project for the subject wireless communications. I'll just begin with the slideshow. Okay, so the name of my presentation for the class project is implementation of speech recognition systems for various applications in cellular communication. So this is the topic of my class project. Now let's have a look at the objectives of the class project. Now, the first objective is to develop a efficient speech recognition software. Now, the purpose is to develop this software and then implement this in a working model, which can be used for exploiting the capabilities of speech recognition for different applications in cellular communication. I will also be analyzing the performance of the software for these various applications under different sets of input conditions. Now, before we start, I would like to talk about what is speech recognition actually. Speech recognition is basically a translation of spoken words into text. It is also known like automatic speech recognition or computer speech recognition. Now, the development of speech recognition first started in the year 1950, but later on in 1990 it was first implemented for applications of cellular communication. Now, the main purpose of speech recognition was basically to generate new revenues by using automated call attendance, and thereby we can remove the cost for human attendance. So, here in this project, I'll be talking about a novel speech recognition technique which can be exploited for various different applications in cellular communication, and this can actually help in reducing the costs of operators and hence generate more revenue. In this slide, we look at a proposed model for speech recognition. Now, this model is basically shows us the working for the speech recognition. The first set is data acquisition. Here we acquire the data, then we send down for denoising, where the noise is removed from the acquired signal. It is then filtered to remove unwanted frequency range noise, and then an average power calculation and framing is done on the signal. After that, it's moved on to endpoint detection. Here in endpoint detection is basically used to extract the speech signal. After this, we do a pre-emphasis, and then we do a windowing on this on the extracted speech signal. After that, a fast Fourier transform is done, and then we have feature extraction, pattern matching. Now, I will elaborate. I will go on describing each and every step much more elaborately in the next few slides. So let us look at the first block, that is data acquisition. Now, data is actually acquired using this MATLAB software. Now, it is actually recorded in a discrete form. The rate of the data that is chosen, the sampling rate, is chosen according to the Nyquist theorem. Now, what does Nyquist theorem tell us? It tells us that the sampling rate of the data needs to be twice the amount, and for twice the size as large as the highest frequency presented in the whole signal. So, if suppose the highest frequency present is 2 gigahertz, the sampling rate needs to be done at 4 gigahertz. Now, for our model, we're doing the sampling frequency, we're taking it to be 8 gigahertz, and the duration of the recorded signal is 3 seconds. Yeah, obviously, you can extend this to much more amount of time, but for simplicity purpose, I'm doing it for 3 seconds, and I'm going to check whether the whole thing works or not. So here I'm showing you two waveforms. Now, first waveform is for the speech signal black, and you can see it's the electronic noise environment. So you have a lot of noise here and there. And the second signal is showing for the signal red, and there's like spiky noise environment. So the purpose is to like we'll have signals which will be like this. So this waveform just shows us what kind of signal actually gets recorded, which we need to process so that the speech can be actually transformed into text format or it can be recognized. So this is just a model representation of what kind of a signal we can expect from the for the input. Next, we are looking at denoising. Now, this section is used so that we can remove the unwanted noise from the input signal. Now, for this technique, I'll be using an efficient noise removal technique called wavelet transform. Now, for my model, I'm using a third level one dimensional wavelet transform. Now, this transformation is performed on the speech signal, and it helps us in disintegrating the speech signal into several layers of details. Now, for details, I mean like these details are then like analyzed and processed to remove the noise from the recorded data. But we do need to remember that wavelet transform is also located in both frequency and time domain. In the waveform here, we can see the top figure is actually the recorded data, and the bottom is this denoise version. So you can see the noise at the start and the end is bit flattened out, and the signal is the noise is actually removed a lot from the signal. It's not really clear though in the waveform, but it actually happens. So no, well, now this actually is like a signal for heritage. Now, if I say heritage, this is what's going to be there for the denoise version 2. Let's moving on to the next section. Now, filtering. Now, filtering is basically done to remove the ambient and unwanted frequency range noise. Now, we use a high order bandpass filter for doing this, and the range for the filter is taking to be like 300 hertz to 3400 hertz. Uh, the equation for the digital filter is provided there, where xn is the input discrete time signal and yn is the filtered output. On the left side, we have a magnitude response of the filter, whereas on the right side, we see a filtered version of the speech signal black. Now, filtering efficiently helps us in removing these unwanted frequency range noises. So, this is quite an efficient technique. Now, next we look at average power calculation and framing. Now, framing is basically done to quantize the speech signal. Now, the speech signal is divided into frames of 10 milliseconds, of 20 milliseconds, sorry. And since we're considering overlapping of different speech signals, so therefore the overlapping frame size is again at 10 milliseconds. Now, if we divide a speech into 20 milliseconds, then the total number of frames that we find is 160. Now, average power calculation helps us in determining it's like it's extracting the speech from the entire recording. Now, when I'm recording it for 3 seconds, I'm speaking one word, but I need to extract the single word from the whole signal, because I do not care about anything that is uh, in front of it or at the end of it. I only need to care about the signal which says, for example, the word black. Now, I only need the recording for the black portion. I don't need the one which is before or which is after. So, average power calculation basically helps us in doing that. The average power of the frames are calculated, and a threshold limit is also determined. Now, we have the equation which shows us where p is the power, and this equation is like p is equal to summation of s of n squared, where s is the signal, p is the power, and capital N is the frame length. So the summation is done till the frame length. Now, the frames which are above the threshold limit are taken into consideration, whereas the signals who are below the threshold limit is rejected. And over here we see the power calculation for the speech signal black. So you can see, if I go back to the previous slide, we see the filtered version of the speech signal, and in this side you can see that the power calculation for the speech signal. Now next going to define the block endpoint detection. Now endpoint detection is the most novel technique in this recognition model that I'm proposing, because in this step we actually are able to completely determine the starting and the ending points of this of the speech portion in the complete signal. Now framing, along with framing and average power calculation and endpoint detection, we are able to extract the whole speech portion from the whole signal. Now, even here, the threshold value is also calculated for determining the starting and the ending points. Now, the speech portion of the signal will always lie above this threshold value, and the noise signal, for example, will be below the threshold value. So on one frame where we have the value is above threshold limit, we will move it up. That means that it is a speech portion, and the one where it is below, we take it to be that it's the noise. Now, for the entire, this signal is actually, this portion is adaptive in nature. By adaptive, I mean, this threshold value is always calculated for every new type of signal. It's not just a predetermined threshold value that I am giving, because a different kind of a signal can be present with different parameters, and this threshold value will again be calculated. When it's calculated, it's going to work for that new set of signals. So by this I can tell you that this endpoint detection is adaptive in nature. That means it provides much more flexibility in our operation of the recognition model. Next, we are going to look at pre-emphasis. Now, pre-emphasis is basically done to ensure that the frequency components do not fall off at high frequencies. Now, by using pre-emphasis, we can absolutely ensure this. Now, the equation for doing this, the filter response equation that does it is defined, where y of n is equals to x of n minus alpha x of n minus 1. Now, the value of alpha ranges between 0 to 1, and it is actually used to control the degree of the pre-emphasis filtering. Now, the value of alpha here is 0.96, and over here we can see the filter response for the pre-emphasis filter, where the first, on the diagram on the left, the first portion is magnitude response versus frequency, and the one below is for the phase versus frequency. And on the right we see the pre-emphasis version of the speech signal black. Now the bottom figure is the pre-emphasis version, whereas the top figure is the extracted speech signal after the endpoint detection. Now if I go back to endpoint detection, you can see just the speech portion is detected, and the noise before the speech portion and after the speech portion is not present. So this section is completely just the speech, and in this diagram that section is zoomed in. And it's plotted. So the top figure is actually just the speech portion that we see here in this previous diagram, which is zoomed in, and its pre-emphasized version is there at the bottom. Next, I will be talking